Hello everyone, welcome to our virtual presentation. I'm Yuxing Qiu and I'm delighted to introduce our newest work on high-performance NPM, a massively parallel and scalable multi-GPU material point method. NPM has become more widely adopted in today's physics-based simulation in both graphics and computational science, but its awesomeness has been greatly hindered by the memory capacity and computing resources provided by the modern computer architecture. The present work is the first to tackle this crucial limitation from a multi-GPU high-performance computing perspective, hoping to leverage the existing supercomputing resources to achieve large-scale offline simulations. This work is a joint effort among UPenn, Zhejiang University, UCLA, Oak Ridge National Lab, and the University of Maryland. To give a high-level overview, this paper develops a more efficient multi-GPU NPM solver capable of handling almost 100 million particles at a speed of 1 minute per frame. The number of the particles handled by this proposed method is almost 100 times more than the previous state-of-the-art methods. Such a level of scale and realism has never been achieved in prior work using NPM. Our secret sauce is a novel reformulation of the classic NPM pipeline with a dedicated new data structure to maximize the computation and bandwidth efficiency. We devised a new G2P2G kernel, short for the grid-to-particle-to-grid kernel, as well as a new particle data structure that is AOSOA, short for Array of Structure of Array. Although it can simulate versatile materials with convincing results, conventional implementations of NPM are inherently both memory and computation intensive. As a hybrid method, NPM requires the correct handling of both particles and grids, making the optimization more challenging. A conventional first-order NPM integration scheme includes 3 basic substeps in each simulation step. That is, first, particle to grid, to transfer particle mass and momentum to grids. Second, grid update, to update grid velocities. And third, grid to particle and particle advection, to transfer updated velocities back to particles and evolve particle states. To achieve high-performance parallel implementation, generally an additional step is needed to maintain the sparse data structure and the partition of particles and grids. That is the partition update. In the rest of the presentation, we use P2G as the short for the particle-to-grid transfer and G2P for the grid-to-particle transfer. State-of-the-art GPU-based NPM implementations use GPU-tailored data structures for particles and grids and customize their computational kernels accordingly. Both works by Gao in 2018 and Hu in 2019 follow the same NPM integration schemes as introduced in the literature. The focus of their work lies in the optimization within each substep. The performance bottleneck occurs in the P2G and G2P kernels, where extensive particle and grid data accesses are involved. In contrast, our work tries to optimize not only the procedure within each substep, but takes a more holistic view by rearranging the substeps. First, we analyze the data dependency among these substeps to avoid as many data reads and writes as possible. The intuition is simple. Reducing data accesses and properly handling data accesses is critical to high performance. As we can see here, both the G2P and the update partition substeps depend only on the updated particle positions. If we were to execute the substeps in the traditional way, we would need to store the updated particle velocities and the C matrix for particle grid transfer after G2P, because these attributes are needed in the next P2G step. But if we combine the current G2P and the P2G in the next time step into a single kernel, this overhead of data access can be reduced. Based on this observation, we reformulate the conventional NPM with a new G2P2G kernel by combining the G2P and the next P2G. During this process, the particle velocities and the C matrix can be computed on the fly by interpolation from grid nodes. In this way, 12 floats can be saved from the memory requirement of each particles. Additionally, the redundant particle data write and read between G2P and the next P2G can be eliminated. Our G2P2G execution scheme works essentially the same as the traditional NPM, but can be understood from totally different perspectives. Traditionally, we make use of O'Leary grids to solve the system, and accordingly evolve the particle states. However, with G2P2G, the particles are treated as the background helpers to solve the material responses and advect the updated grid attributes. The G2P2G approach is not only effective in the explicit integration scheme, but implicit schemes can also benefit. As long as G2P and P2G are both needed for computation, the G2P2G reformulation can be adopted for better performance. To fully exploit the power of G2P2G, we need to make some changes related to particle grid mapping. We here use a 2D scenario for illustration. The state-of-the-art methods use GPU-tailored SP grid and partition the whole domain into 4x4 blocks to manage the background grid. The particles are mapped to blocks with an off-by-one strategy, so that each block of particles only reads from or writes to the 4 neighboring blocks instead of 9. In this way, the limited shared memory can be used to load the grid blocks inside each CUDA block, making the transfer process more efficient. However, this off-by-one strategy is not feasible in the G2P2G kernel, since the particle advection would break the off-by-one assumption. To solve this problem, we propose a new off-by-two mapping strategy. With a CFF-restricted stepping time, particles can move at most a 1-cell distance after grid-to-particle transfer and particle advection. In the follow-up particle-to-grid transfer, the grid nodes these particles may write to can extend by at most 1 cell in each direction. Therefore, the off-by-two strategy can keep the assumption that each block of particles only interacts with 4 neighboring blocks, making it possible to benefit from the CUDA shared memory. Another problem to be solved is the computation of the stepping time in G2P2G. Traditionally, we compute the stepping time from the maximum velocity of particles. This is a piece of global information that cannot be accessed during the execution of G2P2G kernel. Therefore, we compute the stepping time from the maximum velocity of the grid nodes. We observe little difference of the computed $t with these two methods. With G2P2G and these improved techniques, we can achieve almost 1.5 times acceleration compared to the traditional NPM pipeline, even on a single GPU. In addition to the new G2P2G, from a holistic view across substeps, we further improved the efficiency of particle data access with the new data structure. To develop an efficient data structure, we need to analyze the data access substeps and organize data in a way that could efficiently utilize the hardware. In this work, we maximize the performance of the transfer kernels. Before introducing our new data structure, let's first examine the typical ones used in the prior works. The method on the left panel uses a structure of array or SOA layout for SHA. SOA first stores the mass channel of all the particles, then the next channel of all the particles. This layout is ideal for streaming data access on GPUs. When applied to GPU-based NPM, particles are sorted by cell to ensure coalesced data accessing for each blob of threads. To further avoid the writing conflicts during P2G, efficient warp level reductions are performed before writing data back to the global memory. Note that this method requires an additional sorting at the end of each time step. In comparison, the method on the right panel uses an array of structure or AOS layout for SHA. AOS first stores all the channels of the first particle and then all the channels of the next particle. The performance of this layout is less sensitive to the particle order, but has a lower bandwidth efficiency. Particles are left unsorted, which reduce the chance of atomic write conflicts during P2G. To exploit the advantage of both SOA and AOS and allow for the extension to multiple GPUs, we design a new data structure for particles. The design needs to adapt to the G2P2G reformulation such that each warp of threads can access data in a coalesced manner. Each block of particles can reside in a continuous block memory for easier migration between GPUs, and also try to minimize the memory footprint as much as possible. Following these principles, we devise an AOS-OA structure to store particle attributes. The particles are grouped according to their positions, such that the particles mapping to the same block can be gathered together in memory. The SOA layout is adopted to store the particle attributes inside each block, while the particle blocks are organized in an AOS layout. Inside each grid block, we subdivide particles into SOA bins and put particles from different cells into the same bin if feasible. During P2G, these particles will write to the different grid nodes without writing conflicts. The bins in each block are organized in an AOS layout. With this design, particles in the same block are stored continuously in memory and can be efficiently transferred to other GPUs. The size of SOA bins is chosen according to the kilowatt size so that the SOA structure inside each bin ensures coalesced data access, which maximizes the bandwidth efficiency. Furthermore, since the number of particles in a block is dynamic, a large amount of memory would be wasted with the uniform storage of particle blocks. However, with the particle bins, the majority of the memory overhead can be fully avoided. We adopt a hierarchical particle bucket design to implement the mapping from a block to its particles. Specifically, the particle attributes and particle indices are stored separately in particle blocks and particle buckets, both with a 4x4x4 granularity. We use the double buffer strategy to make G2P2G kernel reads from and writes to different particle or grid buffers. Each particle is reached hierarchically through the block index and the local index inside the block. Furthermore, we use the delayed ordering strategy for particles, which postpones the particle reordering in the G2P2G kernel to the next time step. Here shows the timing for both G2P2G and the AOS-OA particle data structure, as well as the comparison to the state-of-the-art single GPU algorithm. We also compare our method with state-of-the-art GPU-based and CPU-parallelized NPM. Our experiments show an over 2 times speed-up on the traditional GPU-based method and 100 times acceleration compared to the CPU-parallelized version. So far, we have seen a significant improvement of NPM on single GPU. Now we take a step further and extend the G2P2G kernel and AOS-OA particle data structure to multiple GPUs. The main challenge are load balancing and communications overhead among GPUs, which requires different partitions to share as little data as possible. We propose 2 partitioning methods according to the material properties. We use the static partitioning by particle scheme for solids and the static partitioning by space for fluids. With static particle partitioning, each GPU handles a non-overlapped static set of particles throughout the whole simulation process, and the halo grid region must be synchronized and reduced to ensure a valid upcoming G2P2G computation. This scheme works pretty well for solids when there are no severe particle penetrations. However, the halo grids would grow significantly for fluids as time goes by. Thus, we adopt a different strategy, partitioning by space, where each GPU handles a static spatial space and transfer particles. Two additional components are integrated for multiple GPUs, that is, the halo block tagging and the halo block merging. Here we focus on the halo block merging task, which is much more time-consuming. We use different CUDA streams to handle computation and data transfer, with CUDA events to mark the beginning and the finish of each step to ensure the logical correctness of the code. With this strategy, the expense of the memory copy among GPUs is largely hidden by the G2P2G computations. In this way, we can maximize the performance as much as possible. To show the efficiency of the proposed multiple GPU algorithm, we present the weak scaling and the strong scaling result here. The weak scaling measures the efficiency by asking each device to handle the same amount of computations and increase the device numbers. The strong scaling is about using different numbers of devices to solve a fixed computational problem. In both evaluation protocols, our method achieves efficiency over 90%. Here we show more results. Here we show more than 6,000 bombs falling onto the ground. This simulation involves 134 million particles and can be finished within 1 minute on 8 GPUs. In this experiment, more than 6,000 candies are poured into a ball from a tube. 23 million particles are involved, and each frame takes only 4 seconds on 4 GPUs. Here we observe from another view. In addition to the elastic material, our method can also handle plasticity phenomena. Here we show a concrete crashing simulation with 93 million particles on 4 GPUs. The right corner shows the GPU partition of the concrete. We color the plastic volumetric strain to visualize the damage propagation on the concrete. In this demo, we show a soil falling test with non-associated camp clay with 53 million particles on 4 GPUs. The damage propagation is shown in different colors. For this experiment, we adopt static partitioning by particles. This slide shows the partition on 4 GPUs. In this simulation, two sand armadillos hug and smash together with 55 million particles on 4 GPUs. Fine details are captured with a small .x. In addition to solids, our method also works for fluid simulation. Thank you.